Okay, so we are recording. All right, so what we're going to look at today is limits at infinity. Now, this is a little bit different from limits that equal infinity. So I'm going to flip it over to Desmos for a bit. I got a couple of graphs in the graphing calculator here. And in Desmos, if you type the word table, it'll actually produce a table of values that you can play with here. So I want to talk about when I plug in 2 into this function, 1 over x minus 2 squared, I get 2 minus 2 is 0, 0 squared is 0. So I have 1 over 0. So at 2 itself, I'm getting undefined. But when I look at the graph around 2, I can see that it's shooting up towards infinity. It's just going to keep growing and growing and growing. But another way to see that, if you don't have the graph in front of you, is you can think about what happens if I plug in numbers really close to 2. So if I plug in 1.9, 1.9 minus 2 is going to be negative 1/10, but squared, it'll be positive 100th. And then we flip it and get the 100. So if I plug in more 9s, we see it grows real fast. So on the left side of 2, when we look at the numbers plugging in, we see the smaller a decimal I plug in, the bigger the fraction ends up being when it gets flipped. So we end up with a tiny, tiny decimal, and then when we reciprocal that decimal, we get an exponentially huge number. And the same thing happens on the other side. When I plug in just 2.1, I get 100. If I plug in 2 point and a whole lot of zeros and then the 1, like here, I've got 1,000,000. So either side of the asymptote, we're getting infinity. But when we plugged in the number itself, we just got undefined. We got a number divided by 0. So here, it's really tempting to say, oh, okay, so when we divide by 0, we get infinity. And for the most part, that works. But check out what happens when I change the function to g of x instead of f of x. So g of x is just 1 over x minus 2. So I'm getting the same thing. When I plug in 2, it's undefined. But on either side of the undefined, I'm getting different infinities. So we need to be able to tell algebraically, which way these infinities are going. So when I plug in a number a little bit smaller than 2, the 1.9, I end up with negative 1/10, and then I'm not squaring it, so it stays negative. But if I made this function up top negative, it flips the whole graph over. Now when I plug in that 1.9, I get a negative number, but the top also has a negative number. So now that's going to flip to a positive infinity. And then on the right side, the 2.1 is going to be positive, but the negative number on top will make the final result negative. So the left side on this graph goes up to positive infinity, but the right side goes down to negative infinity. So we talked a bit about how to pull this from the graph. We didn't talk so much about how to tell from the function formulas. And we're going to see a little more investigation in the algebra, looking at just the formulas and being able to pull this information out. But I just wanted to reinforce this overall idea of if I want to know what's happening at a number for the limit, sometimes plugging in the number itself gives us a hint, but it's not necessarily a definitive answer. Now, if you plug in the number and get a number out, then as long as the graph itself isn't piecewise, typically what you see is what you get. Not always, but typically. All right, I'm going to flip it back to the module. But now, instead of looking at limits as we approach a number that equal infinity, now we're asking, what happens if we send x to infinity? So as x increases without bound, gets bigger and bigger and bigger, what could happen to a function? So what happens to most functions you've seen when x grows and grows and grows? What do most of the functions do? Or some of the functions?
Say that again.
So as x gets bigger and bigger and bigger, what do some functions do? Like what do we often see on just like a regular polynomial? So what's a polynomial? Why is a math question at 10 in the morning the hardest thing ever? So y'all gotta have breakfast before you come here so you wake up a little. Not just coffee, not just caffeine, a little bit of actual food. So polynomials are like x to a power, and then there might be some numbers, there might be some smaller terms, but like x squared is a polynomial, x cubed, 4x to the 7th plus 3x to the 4th minus 7. That's a polynomial. So just x to some power. So as I plug in big numbers into x to the 3rd, what's going to happen to the function? So if I plug in 1,000,000, what am I going to get when I cube 1,000,000? A big number. And then if I plug in an even bigger number, 1,000,000,000, it's going to get even bigger. So a lot of functions, as we look at x going to infinity, we typically get an infinity. We could get a negative infinity. If I looked at negative x cubed, then I plug in the number, I cube it, it's really big, but then there's a negative in front, so it's a really big negative number. So a lot of the functions that you guys have looked at in the past, typically we get this kind of infinite behavior, but there's some functions in particular that won't follow that trend. Specifically, when we look at rational functions. So if we zoom in here, the function equation is 2 plus 1 over x. So 1 over x normally has an asymptote at, this is y equals 0, the horizontal line, the x-axis. But if we add 2 to it, it shifts that asymptote up 2. So now as I plug in increasingly large numbers, like 1 over 1,000, that's 0.001. So I have 2 plus a little tiny number. Now if I plug in 1,000,000, now I've got 2 plus 1,000,000th. It's still a tiny bit bigger than 2, but it's actually even closer to 2 than the previous number. Okay. So as we fill in increasingly larger and larger x values, the graph, the function itself, gets closer and closer to that horizontal asymptote. Now, a lot of functions, when they have a horizontal asymptote, it's the asymptote on both sides of the graph. Not all functions, but most of them, especially when we're looking at rational functions like this, the horizontal asymptote is typically the same on both sides. So as we decrease x, as I plug in increasingly huge negative numbers, I'm going to get 2 plus a negative tiny decimal. So I'll end up with like 1.999 or 1.999999999 or 1 point even more nines. So I'm getting, every time I put in a bigger number, I'm getting that much closer to the function value of 2, the y value of 2. So what we see is when we have this 1 over infinity, that as an idea tends towards 0. Now, if I just had 2 plus x, that guy would shoot off to infinity. As we go decrease x towards negative infinity, it shoots down to negative infinity. But when we have this rational function, 1 over x, we get this weird behavior where it's going to approach a value. So here is our formal definition. But the idea being, as we keep increasing x, the function just keeps getting closer and closer to a fixed number. Then we say that fixed number is what the limit as x approaches infinity of the function is equal to. And then the reverse side is if the function, as x gets increasingly more negative, if it's approaching a particular value, then we say that is the limit as x approaches infinity of that function. So we call this behavior, if the function approaches a value instead of approaching an infinity or a negative infinity, then we call that a horizontal asymptote. Now, for a lot of our functions, it's going to be the same horizontal asymptote on both sides, but not all of our functions. We're going to look at a couple of the other ones that the horizontal asymptote only applies on one side. But let's take a look at this one. So the cosine of x divided by x plus 1. So we're just looking as x approaches infinity. What is this crazy little graph doing? Yep. So as we put bigger and bigger values in for x, the graph, we can see like the peaks and valleys are getting smaller and smaller. So the graph itself is like just decreasing down to that horizontal line. If I look at the function formula, as I plug in infinite numbers, cosine is a weird little guy. It goes up to 1, it goes down to -1, and then it goes back up to 1, and then it goes back down to -1. And it just keeps going back and forth between 1 and -1. So as x goes to infinity for the trig functions, there is no definitive answer because the trig functions are periodic. So they are constantly cycling through values. But when it's being divided by basically any x to any power, those x's on the bottom now have more control over the cosine. So the cosine is just back and forth between 1 and -1, but now the x's on the bottom are like 1,000,000 or 1,000,000,000. And now it's taking that 1 and -1 and forcing it to shrink down to, in this case, that +1 number that we added on the end. So that +1 is just forcing the whole graph to center around the line y = 1 instead of centering around the x-axis, which is the line y = 0. So if we write this notationally, the limit as x approaches infinity of f of x, looking at our graph, equals 1. So since the limit as x approaches infinity is equal to a constant, then yes, there is a horizontal asymptote. Now, horizontal lines are all the points that share a common coordinate. So if I think of points on this line, that's the point 5, 1. If I think of another one, that's the point 20, 1. So what's the same between those 2 points? 1. And then what is that 1? So is it an x or a y number? It's a y number. So these are both sharing y coordinates of 1. So all the points on that line share y coordinates of 1. So the equation of that line is y equals 1. So it's just a slightly different way of getting to what's the equation of a horizontal line or a vertical line. I find a lot of people will mix up, is it an x equal line or a y equals line? This kind of takes a little bit more thinking, but the thinking is very consistent. The other way, like kind of cheap trick way to remember it, is the horizontal line crosses through the y-axis at y equals 1. So there's our equation. It's a y equals 1 number. If it was a vertical line, it's crossing through the x-axis, so it's hitting an x equal line, an x equal number. But for our limits at infinity, everything's going to be horizontal asymptotes here. So we're going to see a whole bunch of y equal lines. Now, in that, we had a discussion about oscillating functions. So if we're just looking at the graph of sine x, like cosine x, it just constantly goes back and forth between 1 and -1. So the limit as x approaches infinity of sine x does not exist. Because it doesn't ever decide on one value. It's constantly back and forth between 1 and -1. All right, now, just like we talked about earlier, if we're looking at a polynomial like x cubed here, as we plug in increasing x values, the function just shoots off to infinity. So the limit as x approaches infinity of f of x, or sorry, let me just write the formula in there, of x cubed will equal positive infinity. Now, if I plug in a negative number into x cubed, I want to figure out, is that going to be negative or is it going to be positive? So if I plug in like -2, what do I get? Yep, -2 would be -8, so we get a negative. So if I plug in -10, I'm going to get -1,000. -1,000,000, I get -1 with way too many zeros. So this one is going to approach negative infinity. And we can see that on the graph. Like it's, especially if you notice here, the y-axis is like much bigger numbers than the x-axis. So another same definition. Now, one of the key infinite limits that we're going to see a lot is this 1 over x. So we want to formally like look at this and evaluate it because we're going to see it pop up inside a bunch of stuff. So the limit as x approaches infinity of 1 over x. So when we substitute infinity, like we have this 1 over infinity, but when we look at the graph, as x gets larger and larger and larger, what is 1 over x going to do? So I think about if I plugged in 100, 1 over 100 is 0.01. But if I plug in 1,000,000, now I'm going to get a lot more zeros before my 1, so 0.000001. Or a billion, like It's an even tinier decimal, a trillion, even tinier decimal. But these decimals are all getting closer and closer to what number? 0. So when we get 1 over infinity, that actually approaches 0. It's approaching 0 from the positive side, but still approaches 0. When we look at the limit from the other side, as x gets increasingly negative, but same function, 1 over x, one over negative infinity, I'm getting these increasingly tiny negative fractions, but they're still those little tiny decimals with all the zeros before we start getting anything. So this is also approaching 0. So the overall takeaway here is when I get 1 over infinity, like even if it was 1 over like x cubed, infinity cubed, it's just going to 0 even faster. Or 1 over negative infinity cubed, it's still going to 0 faster. It's just going from the negative side. So even if we put some powers on that infinity, it's still going to go to 0. So overall, we have this like, if I zoom in and like, because we know limits can go inside division, go inside multiplication. So as I move my limit inside, eventually I can get little fractions like this that'll go to 0. So I can like break it apart. All my zeros I can kind of mark off and then focus on the parts that aren't specifically going to 0 and then see how it all interacts. And I can algebraically figure out what the function is doing as x approaches infinity. Now I know today I can type in and get Desmos to produce a graph and then kind of see what's going on. But a lot of this approach was from when graphing a function involved plugging in numbers by hand, getting the y values and then plotting the point and then doing it again and again. And if you picked the wrong numbers, sometimes you would miss a pattern and then get the wrong graph. So yeah, it gets a little weird. Now for polynomials, so when I have ax to the n, and this is my biggest term, my biggest power term. So if I'm looking at like x to the 7th plus x to the 6th minus x to the 5th plus x to the 4th minus x to the 3rd minus x squared minus x plus 7. X to the 7th has a lot more control over what that graph is going to do than all those other terms as we look when x goes to infinity or negative infinity. Like plugging in 100 to the 7th power is much bigger than 100 to the 6th. Or if I plug in a million to the 7th power is way, way, way bigger than just a million to the 6th. A million to the 6th is still pretty big, but a million to the 7th is bigger by several degrees, like several times 10. So when we're looking at polynomials, even though there's a whole bunch of terms, whichever term has the biggest power is what I call drives the bus. It's what's determining overall where they're going. So it's kind of like the parent in the car saying, all right, where are we going? McDonald's, Burger King, Wendy's, Whataburger. I'm the parent, I'm driving, I decide where we're going. So what we're going to look at here is, so what happens, that biggest power, where it goes, depends on whether the power is even or odd, and whether the coefficient in front is positive or negative. So most of the functions we look at, the coefficient is positive. So when the coefficient is positive, then the behavior on the right is going to go up to positive infinity. When the coefficient is negative, then if I plug in like a million cubed, but it's times a negative number, it goes negative. If I plug in, sorry, I said cubed. If I plug in 1,000,000 to the fourth power, but the A is negative, it's going to force it to go negative. So that's our behavior on the right. If our coefficient is positive, then our behavior on the right is positive. If our coefficient is negative, then our behavior on the right is negative. Now, the even versus the odd determines what the left side of the graph does. So when n is even, like x squared, then the two sides of the graph go in the same direction. So we know x squared, like both sides of the parabola go up. X to the fourth might have a little bit of wiggling in between, but both sides of the graph will go in the same direction. The same with x to the sixth, x to the eighth. All of those even powers, they both will either both go up or both go down. And then I kind of put this weird like squiggle in between to say like the graph might squiggle around in between, but here's what the very outside end values are. Now, if n is odd, like x cubed, x to the fifth, these do opposite behaviors. So I still have that potential for squiggling, but it's going to go in the opposite direction from wherever it's ending. For a lot of these, though, I find if you just think about very basic functions, that can help you remember like what's going on. So like n is even, that's like x squared. And then if it's positive versus negative. So those guys are placeholders for what every polynomial of even or odd degree with positive or negative coefficients will do at the extreme values, at positive infinity or at negative infinity. So what we want to look at now is we're going to look at rational functions, but most of our rational functions are just polynomials over polynomials. So if I can remember what's happening on the polynomials as x goes to infinity, then I can come back to the fraction and my individual little fractions, 1 over infinity or 1 over negative infinity, those are going to go to 0. So I'm going to combine these two ideas to start evaluating some of these crazy limits. So I'm going to look at the limit as x approaches infinity of our function 5 minus 2 over x squared. So the limit of a constant 5 is a constant. So I can distribute this limit like across the minus sign. I can distribute it on the top and the bottom of the fraction. But all the constants are just going to go where they say they are going. The limit of a constant is just the constant. So the only thing that like does anything interesting with the limit behavior is that x. So I'm going to like zoom in the limit to 5 minus 2 over the limit as x approaches infinity of x squared. So as x approaches positive infinity of x squared, what does x squared do? Yep, it's going to approach infinity. So infinity squared is just even bigger. So this gives us 5 minus 2 over infinity. Now, a constant divided by infinity, as long as it's a constant, is the same as 1 over infinity. So 2 over infinity is going to do the same thing as 1 over infinity. This part here is going to go to 0. So our overall limit is approaching 5. And that's the behavior we were seeing earlier. We had like a rational function, and then we added a number to it, and it shifted the whole graph up. So that's what's happening here. We have a weird rational function, and then they've added a 5. They happen to make the rational part negative, but the 5 is what determines what happens at the end values here. Because the rational part just ends up going to 0 when we look at those extremes. Now, if I do the limit from the other side, the negative infinity, for our rational functions, typically you're going to get the same thing twice. So on your homework, you may not bother writing it all out. But on the test, if we ask you to evaluate both limits, you do need to write it out. So as x approaches negative infinity of x squared, so think about our graph of x squared. It's a parabola, right? So as x goes to positive infinity, it shoots up. As x goes to negative infinity, it shoots up. So the limit as x approaches negative infinity of this, it's still going to infinity. So we're getting that 5 minus 2 over negative infinity squared will approach positive infinity. But then there's the minus sign from the formula. But it's still a constant over infinity. So this is still going to 0. So we still get the 5. So that 5 is the horizontal asymptote of this graph. Now, what about if we look at sine x over x? It's a little bit crazier. So I'm just going to distribute the limit to the top and the bottom. And this is not necessarily a step you have to write out, but it should be a thought you're having as you're doing these initially. So on the bottom, that one's more familiar. As x approaches infinity, what does x do? Also approaches infinity. So on the bottom, we're heading towards infinity. Now, what happens on top? Yes, the limit as x approaches infinity of sine x does not exist. But once we have it as a fraction, like here, we're thinking this guy is constantly going between -1 and 1. So it's an oscillating function, but it's never oscillating to an infinity. It's always some sort of constant number. So any sort of constant divided by infinity goes to 0. Now, if it was some other trig function, like cosine would also go to 0, but if it was any of the other guys, all bets are off. So the limit as x approaches negative infinity of this same sine x over x, we're seeing that same behavior. The top is still oscillating between -1 and 1, but the bottom is going to negative infinity. But it's still a constant number over infinite behavior, so it's still going to go to 0. All right. So sorry, like, what questions do y'all have on this one or anything so far? All right. This one's going to be a little more interesting. So when I start out and I just try to plug in my infinity, I essentially get this, which is infinity over infinity. Infinity over infinity is what we call an indeterminate form, because we don't know, as weird as this sounds, which infinity is bigger. Like, which infinity has more control over this double-decker bus. So when we get infinity over infinity like this, then we've got to go back to the drawing board, reconsider some things. But overall, this is a fraction. So anytime I have a fraction, I can multiply by a creative form of 1 and change the format, the structure, without changing the size, without making it bigger or smaller. So let's rewrite that. So when we're looking at the structure and we're figuring out, like, what do I want to do here? Now, if I think about the way these two things graph, like the top is a line with a slope of 2 and an intercept of 6. The bottom is a line with a slope of 5 and an intercept of -1. So if I think about, like, how fast these guys are going, they're both being driven by an x. So they're both going at about the same pace. The slopes are a little bit different, but overall, this idea of, like, who's got control of the bus, they both have the same amount of power. But it's really hard to tell, like, what's going on because those x's just show us this infinite growth. But what if I could get rid of that x there? So I have 2 times x. I don't want to see the x there anymore. So one of the ways we would get rid of that is by dividing by x. Now, I can't just divide by x in one spot and call it good, but I can divide the top and bottom by x. Now, we usually don't write it out that way, though. What we write is multiplying by 1 over x on the top and 1 over x on the bottom. I'm choosing 1 over x because x is my highest power term. So when I distribute that 1 over x through, 2x times 1 over x, oh, let me rewrite the limit, will just be 2 now plus 6 over x. And then on the bottom, we'll have 5 minus 1 over x. So now if I move my limit as x approaches infinity and now evaluate this, now I've got 2 plus 6 over infinity and 5 minus 1 over infinity. So what happens with the little 6 over infinity? Yep, it's going to go to 0. What happens with my little 1 over infinity? Also goes to 0. So we end up with 2 plus 0 over 5 minus 0. And we get 2/5. So it turns out, like, kind of thinking about the structure of the problem, the x's they have the same power. So it drives this whole thing towards the constant 2/5. Now, back when you guys did college algebra or maybe some of, not pre-calculus here, but pre-calculus in high school, they'll sometimes cover functions like this. But they'll talk about, like, where's the highest degree? Is it on the top? Is it on the bottom? Are they the same? If they're the same, it's just the coefficients. This is just a different way of getting at that same information, but with less bullshit memorization. Like, the way they explained that wasn't wrong. It was just, to me, kind of annoyed me because it was a little too dependent on, like, thinking of cases without a lot of thought behind why the cases are the way they are. All right. So let's take a look at this crazy mess. So we have the limit as x approaches negative infinity of a polynomial over a polynomial. So there's kind of two ways to go about this. One way is, especially when you're looking at polynomials, like, it really is about who's driving the bus. So on our top polynomial, what's our strongest, like, who's our most powerful driver? Yep, the 5x to the fourth, because of the x to the fourth. Who's driving the bus on the bottom? Yep, 5x to the sixth, because of the sixth power. So one of the cheap shortcut trick is we can say this weird annoying fraction is similar to, and especially for the purposes of limits at infinity, it's similar to 5x to the fourth over 5x to the sixth. Now that fraction, now that I don't have all the other terms, I can actually, like, just reduce that as a fraction. And I'd end up with 1 over x squared. So the limit as x approaches negative infinity of x squared, like, we'd have 1 over negative infinity squared. Negative infinity squared would be positive infinity. So we have 1 over infinity, but that is still going to go to 0 because the bottom has more power than the top. So even though the top is trying its hardest to try to pull this in a different direction, the bottom is like, I'm bigger, we're going to 0. Whereas the previous one, they had the same power, so we ended up at this weird compromise where we kind of tried to do what they were both saying, and we ended up at 2/5. Now, from a technical standpoint, this is a shortcut, so it's kind of cheating. The technical way to work this one out and I'm going to rearrange the top because I like my biggest power in front. Like, I like shortcuts, but very often shortcuts only work in certain scenarios. So here we're going to do the same thing we did on the previous one. We're going to multiply by a weird looking form of 1. The power we want to choose, though, like it doesn't have too much difference if you pick the biggest power overall or if you just pick the biggest power on top. You're going to end up at the same answer. You just might end up like inverting a fraction twice, depending on which one you pick. So I usually just go with, like, when I'm looking at my two biggest terms, I'll go with whichever power is smaller of the two. So I'm going to cancel out x to the 4th. So 5x to the 4th times 1 over x to the 4th is going to be 5 plus, this will end up being 10 over x to the 3rd minus 1 over x to the 4th. And then on the bottom, 5x to the 6th times 1 over x to the 4th, that's still going to be 5x squared plus 4x plus 7 over x cubed. Now, all of my terms that are number over x to the something as x goes to an infinity or a negative infinity, all of these are going to go to 0. My 5 is going to approach a constant. So on top, I have a constant plus 0 minus 0. So the top here is going to a constant. The bottom, though, when I plug in negative infinity squared, I get positive infinity times 5. I'm going to overall get infinity. It'll be positive infinity minus a smaller infinity plus 0. Overall, it's an infinity. So we get that same result of 0.
Does the shortcut get credit on the test?
Yeah. But the shortcut only works if it's a polynomial over a polynomial. I don't know if it'll be a polynomial over a polynomial on the test, because we're going to see some more where they're not. So I haven't written the test yet to decide which way it's going to be. There are definitely limits at infinity on the test, though. Like they did that in the fall, so that's consistent. How am I doing on time? All right, let me scroll a bit, double check how many we got. All right. So now when we look at this one, they're asking us to evaluate the limit as x goes to positive infinity and the limit as x goes to negative infinity of this rational function, polynomial over polynomial. So our negative 4x to the 5th is our highest power term on top. 2x cubed is our highest power term on the bottom. So overall, this rational function is going to behave like the rational function of those two. In particular, it's when we're looking at limits at infinity, we can like simplify it down to just who drives the bus. If we're looking at any sort of limit that's not infinity, you need to play around with the whole function. So we end up with negative 2x squared. That's overall what this thing is going to behave like on the endpoints. There might be some weird asymptotes in the middle, but overall in the end, it's going to do whatever negative 2x squared does. So when I plug in infinity into negative 2x squared, I get negative 2 times positive infinity squared. So infinity squared is still infinity, it's positive, but then times negative 2 is going to give us negative infinity. So as x goes to positive infinity, this graph is shooting off down to the right towards negative infinity. Now, when I look at negative infinity, I'm still looking at that same negative 2x squared. So I have negative 2 times negative infinity squared. Negative infinity squared will be positive infinity, so I'll have negative 2 times infinity, but the negative 2 is going to make this go to negative infinity as well. So we got a kind of summary slide here. If the highest power term is on the bottom, then the whole thing ends up going to 0. If the powers, the highest powers on the top and the bottom are the same, then we end up trying to do a meet in the middle where the coefficients are actually going to make us go to a weird number. If the largest degree is on top, then we're either going to go to a positive infinity or negative infinity. It just depends on what the overall degree is. So you have to plug in the infinities to see if it was a squared or a cubed. Like, you just have to be careful with that. All right, now this one here, we're looking at the limit as t approaches infinity. And I've got some polynomial terms, but I also have some annoying trig function terms. So as it stands right now, like if I tried to plug in the infinity, I get 8 minus 9 infinities minus sine of infinity over 4 infinities plus cosine of infinity. So we're getting infinite behavior, and then sine of infinity and cosine of infinity, like they just oscillate. So overall, we're still getting infinity over infinity. So like direct substitution doesn't help us out, because we're seeing there's the 9t, negative 9t, and the positive 4t. Like both of those are the same exponent, so they're having some control over the bus. But then we have these weird trig functions that it's like, I don't know what those are doing to the bus. So here, though, still the same idea. The polynomials, especially since we know sine and cosine just oscillate back and forth from 1 to -1. On their own, the sine or the cosine is enough to like mess with the graph. But here, since it's a fraction, we're going to do the same trick where we multiply by a weird form of 1. So let me rewrite the function. So I'm still going to focus on the polynomials here. So my highest power is just a t. So I'm going to multiply by 1 over t on the top and the bottom. So now I have a whole bunch of little fractions, but like 8 over t, as t goes to infinity, that guy's going to 0. My negative minus 9, that's a constant now, so it's going to approach minus 9, minus the sine t over t. We did actually look at this earlier. The sine t as t goes to infinity is a constant over the t will grow without bound. So the t on the bottom will force this whole fraction to go to 0. The same with the cosine t over t. That's going to also force that little fraction to 0. So in the original, when it was just the sine t, like that creates a problem. But when we put it over t, now that thing goes to 0, and we know it doesn't have as much control as that 9t does. So our limit here, we end up with negative 9/4. So sine and cosine don't have as much power as our polynomials, because the polynomials grow without bound to either infinity or negative infinity, and the trig functions are just always stuck between 1 and negative 1. So questions on that one? Still a similar strategy, but we had those trig functions and they're making it a little weird.
There's think that time there's infinity meter automatically going to 0.
So if the top is not infinity, yes. So if the denominator is infinity and the top is a constant, yes. Constant over infinity, like number, just a physical number, like 7 over infinity goes to 0. Negative 2 over infinity goes to 0. If it's an infinity, then we have to play around with it and see like what's going on. Because if I have, like we saw here, when I plugged in the initial numbers, I got infinity over infinity. And we ended up with an answer of negative 9/4. So I didn't get 0 and I didn't get infinity. I actually got some other number. But if I had made the bottom 4t squared, that would have forced the whole thing to go to 0. If I'd made the top negative 9t squared, that would have forced the whole thing to go to a negative infinity because it's a negative 9. So it very much depends on like who's driving the bus, who's got more power. It is 11 o'clock if y'all, I am recording the class, so. All right, so our next piece, the limit as x approaches infinity of 5/6 of e to the x. And then we're also doing the limit as x approaches negative infinity. Now, e to the x is an exponential growth function. So the normal e to the x, as x approaches infinity, it goes off to infinity. As x approaches negative infinity, it goes to 0. So here, now we're looking at numbers, constant numbers raised to an infinity. So here, our knowledge of the exponential graphs is going to come into play here. So looking at my behavior on e to the x, and then this is just a constant being multiplied to e to the x. It's a positive constant, so this limit here is the same as, I can just pull the 5/6 outside of the limit. And I can just use my knowledge of the original graph. So the limit as x approaches infinity of e to the x is infinity. 5/6 times infinity is still infinity. Over here, same thing. I can pull my 5/6 outside of the limit. Now, when I plug in a negative exponent, e to a negative power becomes a fraction. So it's 1 over e to an exponent. 1 over infinity, so this goes to 0. So we can see that from the graph, but we can also, just remembering our exponent rules, also think through what the exponentials are going to do. So let me do it a little more. So this is 5/6 times e to the negative infinity. Negative infinity, like e to a negative power, is the same as 1 over e to the positive power. And now e to infinity would go to infinity, so this becomes, 1 over infinity, which is 0. So that's just like drawing out what I was saying when I was writing before. So if you remember the graph, you can use your knowledge of the graph. But if you also just remember, like number to a positive number gets big, number to a negative power is the same as a fraction, and then we're just using our 1 over infinity knowledge, that goes to 0. Then there's this one. So one of our rules with limit evaluating was if we have a composition of functions, as long as the functions are continuous, I can move my limit inside the functions. So even though we're looking at limits at infinity, like the functions, these functions overall, well, not overall, they're technically not defined at 0, but everywhere else they're defined. So when I look at e to the 1 over x, the limit as x goes to infinity, that's the same as e to the limit as x goes to infinity of 1 over x. Like I can move the limit inside the power. And then the same with my sine function. So when I'm looking the limit as x goes to infinity of 1 over x, that is 1 over infinity. So this little limit here goes to 0. So I have e to the 0. Then we end up with the same limit inside the sine. The limit as x approaches infinity of 1 over x. 1 over infinity would go to 0. So we have e to the 0 times the sine of 0. So what is e to the 0? Yep. What about sine of 0? Do we remember? So which one? Is it 0 or 1? One of them's 0 and one of them's 1, but we got to remember which one's which. So I'm going to give y'all a different way to remember it. Do we remember which one of those is which graph? Yep, the bottom one is cosine. So what does that mean the top one probably is? Yep. So those are the graphs. You can use the graphs to remember, especially what I call the cardinal points or the quadrantal angles. So sine of x, when x equals 0, where's the graph? At 0. Cosine of x, when x is 0, where's the graph? At 1. So cosine of 0 is 1, sine of 0 is 0. So we end up with 1 times 0, we get 0. Now, how else could y'all have figured out what sine of 0 is? Like, do you have any tools that could have helped you figure it out? Yes. I say this because your brain will sometimes get hyperfixated on, I should know this, I should know this, I should know this. Why don't I remember it? And you're just spinning your wheels, and it's like, your job is not to remember all the values of trig functions. Part of your job is to remember the calculator has all of that data stored on it. So you can't just type it in. What's the sine of 0 again? 0. Cool. Now we get the calculus professor's favorite function for limits at infinity. Because the limit of tangent, the graph of inverse tangent of x has asymptotes, 2 horizontal asymptotes. So this is a graph that the limit as x approaches positive infinity is different from the graph as x approaches negative infinity. So for tangent, inverse tangent of x, as x grows and grows and grows, inverse tangent approaches pi over 2. As x gets more and more negative, inverse tangent approaches negative pi over 2. So we're going to see that, like, that typesetting is god awful, though. That is a negative. Now, this particular limit here is a little more interesting. It's asking the limit as t approaches 0 from the positive side. Not what I wanted. So I can move my limit inside. So I'm looking at the inverse tangent of the limit as t approaches 0 from the positive side of 1 over t. So we've got the graph here to help us out. So 0 from the positive side. We're coming into 0 from the right. And then what is 1 over t doing as we come in from the right? So the function values get bigger and bigger and bigger of the graph of 1 over t. So it's going to shoot up to positive infinity. So now we're looking at the inverse tangent as we go towards positive infinity. So as we go, as x increases and increases, the function doodles in and gets closer and closer to the upper horizontal asymptote. So we didn't do a lot of work with inverse trig functions in pre-cal, but this was one function that I was like, this function is going to show back up next semester in calculus to annoy you. This is where it's showing back up. The good news is it doesn't really show up again after this until we get to really, really annoying derivatives. So this isn't so much like, could you do this without looking at the graphs? But now that you have the reminder of the graphs, does this make sense? How we got pi over 2. Like that's what I'm looking for you guys to get out of this. All right. Last one. We're looking as t approaches negative infinity of this weirdness. So if I quote unquote substitute in negative infinity, I'm going to get e to the 3 times negative infinity. And then we have inverse sine of 3 over negative infinity. All right, so our e to the 3 times negative infinity, so this is e to the negative infinity. So e to the negative infinity, that's where this is 1 over e to the infinity. E to the infinity grows without bounds, so 1 over infinity would be 0. All right, now we're going to look at what happens with our inverse sine here. So inside, 3 over negative infinity. That's a constant over infinity, so that's going to 0. So we really are asking, what's the inverse sine of 0? And when we look on our graph for inverse sine, yeah, inverse sine of 0 is 0. So I ended up with 0 times 0. 0 is my final answer here. Now, we very deliberately looked at as t approaches negative infinity here. If we were looking at as t approaches positive infinity, we would get infinity times 0, and then it would be a, I don't know how those interact. And we would use a skill that we haven't learned yet. So there's just our summary of what we learned. If you have taken calculus before and you have learned L'Hopital's rule, yes, L'Hopital's rule applied in several instances in these things, but you can't use it on the test. So you got to remember how to do this by hand. Let me